Good morning, everyone. Welcome to Aqualis Braemar LOC's October 2021 market briefing. For those of you joining online, we're just waiting a couple of minutes for everyone else to join us in the room, so please bear with us. Morning. Good, thanks you. Is anyone else out there? Can you check? Can you just see if anyone else is coming in? Okay, all right, thanks. Good morning, everyone, and welcome again to the Aqualis Braemar LOC Group's market briefing for October 2021. Again, we are live at the old library at Lloyd's of London. We're very pleased to be back in person, and thank you all for those in the room for coming along and joining us today. If your journey was anything like mine, a few people's trains have had it this morning, so thanks for making the effort. And thank you all to those of you who are continuing to join us online to catch this briefing. Just a few notes on some housekeeping. This briefing is accredited by the Chartered Insurance Institute, and delegates can claim up to 1 CPDR for their participation. We will therefore keep a record of those of you logging on today, as well as those of you in the room. Please contact any of us afterwards if you require a certificate for your attendance. I'm delighted to announce our panel today. We've got 2 people speaking after me. Sen will be presenting our technical topic this month. Sen is ABL's Regional Director for DP and Critical Systems for Europe and Africa. An electrical engineer, Sen has significant seafaring and onshore experience working with all kinds of DP systems and specialising in FMEA and FMECA. And I'm really pleased to have him join us today to share his knowledge and experience on the emerging technology of maritime autonomous surface ships. Wei Yang will be presenting the case reports after Sen's done with the technical part of the presentation. Wei Yang is a marine civil engineer and he's a consultant with us in our London office. We're very pleased to have Wei Yang back with us again today. Just another quick note, of course, the usual caveats apply, Chatham House rules apply. The information contained in these presentations and any opinions or comments expressed by myself or my colleagues are those of the presenters ourselves and not necessarily those of ABL. So now I'm going to pass over to Sen, who's going to talk about the learning objectives and carry on to our technical presentation. Thanks, Sen.
Good morning all, and thank you, Mark, for the nice introduction. Should be okay now. Yeah, yeah. Thank you very much, and then good morning to all, and then you are very welcome to the Mark could brief him today, and also those who are joining remotely from online. Yeah. Okay. Today's presentation is the risk. We'll talk about the risk, yeah, system failures and things like that. Those risks that are associated with new concept, emerging concept of autonomous ships. And let's go to the next one. Yeah. So today we'll be discussing. I'll be presenting on the introduction to MAS. What is MAS? Maritime Autonomous Surface Ships, and also some description about the current autonomous automation level of the vessels, and the brief discussion about the dynamic positioning vessels and their automation system. And the risk, again, that main topic is the risk associated with the system failures of these vessels. And then the conclusion. Yeah, let's have a look at actually what are the ships that are going to be built or being built uh, on with related to the autonomous concept. So the first one you can see here is the I think this was started sometime in 2017 or somewhere. This is a container vessel, autonomous container vessel. It's got 79.5 meters long, and then it's a diesel electric propulsion and hybrid, actually battery diesel hybrid. This is another technology, but unfortunately today I don't have much time to talk about these hybrid systems, but that's another emerging technology. So the MAS will be having integrated systems like battery powered, and then the other thing. And there's another company called Armada Fleet. Actually, they're building a lot of vessels. As you can see, there are four DP1 vessels. They're about 21 meters long, and 5 vessels of DP2 at 36 meter long, and then 8 vessels at 78 meter long DP2 all. And then there's another company in Belgium called Anglo Belgian company, and this is a solo mass. It's a container carrier, but working within the uh, uh, waterway, inland waterway thing. It's not going to ocean. And it's also 95 meter thing. And there's another company called Seakit. So they are basically going for hydrographic survey vessels, and they are building about some vessels, various vessels up to 36 meter long. And then Fugro is another company which is building some vessels of autonomous. That is, the range of length will be about 8 meters to 18 meters. And then there's another one called HydroServe. So they are building very small survey vessels up to 5.7 meters long. Right. So these are actually some of the vessels that have been under construction, that have been under construction. Right. Let's talk about what actually MAS is, a maritime autonomous ship, why they need for the industry. So as you know, the technology is developing very fast, and this is an emerging technology. This is a MAS concept. So the, the main idea is to operate these vessels economically, and then safely, and then thing. So the best thing is actually to get rid of the crew on board, or operate these vessels without any people on board. And then, as you see in this photograph, there is a remote control center, and these are the vessels. These vessels will not have any people on board to maintain the system, and this will be monitored or controlled by this remote control center or centers, depending on the configuration of the vessels and things. And then in order to have these vessels working, need to have very good automation system. And some of the systems that I recognize to be improved or analyzed or assessed to see whether the current systems are good enough or we need to improve more into that. So these are the things, remote monitoring and control system that will be done from the remote control station, and integrated automation system. That means all the systems have been integrated into one common system. They have a common platform we call distributed control system. So from there, uh, one person can see everything on the vessel. They are integrated. And then the communication from ship to shore, that is very, very important. Without communication, the controllers, the people in the remote control center will not be able to have any communication with you. That is just important. And also the weather condition. The current days now, the weather conditions, the people on board can see and then alter the course and things like that. The person in the remote control center should be able to understand the weather condition and then change the route and things like that. This is a vast area actually. I'll not be talking much about this area. Within this half an hour, we'll not be able to talk all these things. Right. So based on the system design, the IMO has categorized 4 levels of autonomy. The first one is the first degree of autonomy vessels will have crew on board, and some of the systems are automated. They can take decisions, monitoring everything. So this is basically, these kind of vessels are still available in the industry. So they are not called autonomous, but it's there. And the second degree of autonomy is crew is on board, but vessel will be controlled from a different location. For example, another mothership at sea or shore-based station. So that's another one. But the crew is on board to take action, so attend any repair or anything, any failures, things like that. That is okay. And the degree 3 is a remote operation without any people on board. So the ship will not have any person to attend any repair or configuration or attend any alarms or anything. Everything will be monitored from the remote control station. And I will talk more about this area because this is the main area of topic today, degree 3 autonomy. And degree 4 is fully autonomous. That means no people, even the remote control station will not take any control or anything. They are only monitoring. So the ship has the intelligence to take its own decision based on the weather conditions, failure conditions, and everything. Right. Now, the UK Code of Practice, actually, there is a group in the UK called regulatory, the UK Reg, the regulatory work group formed by many clever people. So they have categorized the UK operation areas up to 7 categories. So you can see there, the unrestricted area is termed category 0. That means these vessels can sail anywhere in the world. So there is no restriction, day or night time. So I'm not going to go through one by one just to save time. So you can see that this are available in UK reg, the code of thing. And the second thing they have introduced is also the weather condition. So the vessel, when it goes to sea, it has to have kind of tolerance of the weather condition. So there's four categories. They are in ocean, offshore, inshore, and sheltered waters. So based on the wind force and the wave height. So these are the 4 categories and things. Okay, let's think about what is needed actually now for a vessel to be controlled from a remote station. So I talk about now degree 3, no people on board, and we need to identify what are the systems that have to be improved or upgraded, or are the current systems of some of the vessels are suitable for this. So in order to do that, I would say that some of the areas that I would consider is a remote control center facilities, and these are not actually visible yet. So this will come with the course of time, and proper data communication system between the two, like RCCs and in the vessels, and the availability of the control and monitoring facility at the RCC. The person who is handling the vessel should be able to see what is happening on the ship. It's not just driving the ship using the thing, but we need to know the status of machinery, alarms, system failures, and things. Those things need to be revisited and see whether the current facilities are enough or they want to improve things like that. And also, the people operating at the RCC should be able to understand navigation as well as the machinery part. If you look at a ship, there are so many clever or skilled engineers on board and the deck officer. So all the engineers and the deck officers are going to be away from the scene, and everything is on the autonomy or the system reliability. So therefore, the system has to be really designed to meet those things. So these are the challenges, I think. And then those things are not yet available. What are the systems currently being built? So those are not yet available. So even the rules are not revised to cope with those things. Class is busy. A lot of classification societies are busy in updating their rules. And IMO is revising their code, STCW and things. So these are under process of updating. So it will take some time to come. Even the design criteria are not visible to us. Very little information, to be honest. Yeah, and the capabilities. Yeah, some of the capabilities of the automation systems. Just some of the systems I'm talking about. On a ship, we have a power management system. I will talk more about these systems with the course of the presentation, but power management system and the integrated automation system, integrated bridge, and the redundant propulsion control system, and dynamic positioning systems. So these are already in existence. These are all, some of them are fully semi-autonomous, some are automated, and then so this, the level of their capabilities have to be as reassessed, and then see how much they are suitable for the requirement of mass. Yeah. So now I talk about the DP. I'll give a little bit of information about DP. There are three categories of DP at the moment: dynamic positioning vessels. One is a DP1. So what a dynamic position ship is? A ship that can stay in one location, position, and the heading can be automatically controlled. That is what is actually dynamic position. Everything is automated, and once the system is given an order, okay, you stay in this position, latitude and longitude, the vessel is capable of staying in that position if it is operated within the capabilities of the vessel. Is a big subject actually, but I cannot tell everything. Now, depending on the weather condition, the thrusters, the vessel propulsion system can act against the resistance coming from those areas. So the vessel stay in position, the system is automatically taking care of, but the people are on board and they are looking at the system failures and reconfiguration and things. Like if something goes, the DPO can, DPO means DP operator, can take control from his local operator station. And DP1 is actually a single failure in any system, static component, or no, the active component can lose the position. That means it can fail. It can have blackout. There's no power at all, like that thing. So that kind of thing. And DP2 is a redundant system. They have two systems at least, two or more systems. If one system fails, the remaining systems will be able to maintain the position under the current state. That is DP2. And DP3, the difference is, it is the same, but the difference is the failures consider a loss of a compartment or static component. In DP2, we don't consider the failure of static component. So that's the difference. So if a ship has a collision and we lose one compartment, so due to flood, the remaining part should be able to maintain the position until you go to a safe location. So that's the requirement of DP3. So this kind of level of autonomy or the automation systems are available currently in the industry. And the next one is a redundant propulsion system. They are not dynamic positioning vessel, but they have two systems, propulsion, independent. If one fails, the other one is there. It can still maintain the speed and the heading of the vessel, but not at the same speed as two propellers, but at least it is safe. So that is, they have these notations given by the class. So class review these systems and issue the notation. It's not that, don't get wrong, not all the ships are given with this redundant propulsion. There are specific vessels which are given this notation. For example, LNG carriers. So they have this redundant propulsion. They have the notation. So this sort of thing. Yeah, just look at vessel. No, this is a, I mean, most of the people know actually what a ship is, but this is a simple overlay of a propulsion and the power system of a vessel. So as you can see, there is one main propeller, and there's another one here, two propellers. That's a port, and this is starboard, this color see, and then two bow thrusters. So this configuration can be used for DP as well as normal sailing. So also you can see the power system for this thing, and there are two switchboard. One is red, yeah. This is the port switchboard. This is the starboard switchboard. The port switchboard is fed by two engines, yeah, or diesel generators. So these two are feeding. This system is independent, and similarly starboard side also independent. So that's how uh, it works. And the system, there is, you know, the center part. This is called the bus tie circuit breaker. So this can be closed or open. This system can be operated with closing this or open this. If it is closed, and there are a lot of protection system needed for the to ensure that the single failure will not cause black out the entire power system. So therefore, the classification societies, they check whether this is in compliance with those types, and the third party is right in the failure analysis. So they do the analysis and see whether this is uh, got sufficient protection. And then after that, there are tests to do that. Yes, let me explain a little bit about remote propulsion control system. That is not actually this remote, but remote from the bridge of the vessel, which is again local. This is not anything. And if you can see here, there are two propellers, as I said in the previous one. These two propellers are controlled from the bridge to maintain the vessel speed. And how they are controlled is a cascade control system, basically. This is the main part. They call there are various names there, the redundant propulsion or integrated propulsion or remote propulsion. All names are there, but the function I will explain a little bit. And these two propellers, it can be used to increase or decrease the speed by varying the speed as well as changing the pitch. By doing this, what we are doing is changing the thrust of this particular propeller. When the thrust is increased, the vessel will go fast. When the thrust is reduced, the vessel will slow down. So that's the combination of this thing is doing that. So this is called VFD, called variable frequency drive, along with the drive control unit, drive control system, and these two will change the speed, and the other one is the pitch control. The pitch of the propeller is controlled by this unit. So this unit get the control from this local controller unit, this one, and then similarly on the starboard side. And then this unit, this is the remote control system on the bridge. So now it is giving the command to this one to control. If any single failure happen, if for example you lose the complete system, but there is another propeller as I mentioned before, so that will maintain the speed and the heading. There's another system, steering system, I have not shown here, but that is also to be controlled. Just to make it simple, I put only the propulsion control here. And now the challenge is, when there are no people on board, how we are going to handle this vessel remotely? What are the information that have to be transferred to the remote control center? This is a wide actually area to discuss, and the need to be done and to have gap analysis to see the current system and what are the things that to be uh, shifted to the remote control. What are the information that have to be available? It's a vast subject. It is, I think it's happening. The industry is clever, the designers are clever, and the research are going on in universities and things like that. So this will come. The technology is very matured now, so these things are possible. And the second one, I'm going to show a diagram of DP vessel, dynamic position vessel. This is a DP2 vessel basically. This system has basically three independent control systems, as you can see. DP, and the other one is IJS, independent joystick. So that is totally independent of the dynamic positioning system. And then the remote, the propulsion system. This is what actually I showed in the previous slide, the remote control. This control system is totally independent of the other two. And you can also see these four boxes. They are called field stations. Each field station controls one thruster or propeller. So this field station will send the command to that particular propeller or thruster to what speed, what angle it is to be. So that is basically local. These are local control. And then through the network, this it will get the signal from either from DP, IJS, or propulsion system, depending what system is selected. So the operator on the ship has the facility to change which system now we are going to use. So this is a very safe system, to be honest. So if a complete DP system fails, and then we have an independent joystick that has the capability to maintain the automatic heading and manual positioning. So it is safely the vessel can go away from the danger area like this. Even the remote propulsion control system can be used to go away from this one. We call independent thruster control because these are thruster control because not only the propulsion, this unit can control also um, the thrusters. So these are three independent. It's very so far this has been working very good with few incidents, of course. But system is matured. So this again now if the DPE system is going to be operated remotely from the remote control center at DIG-D3 autonomy, and then we need to revise and then see what we have, the systems available, what are the things to be done. Again, it's a vast area to discuss. Right. Just to give an idea about a switchboard, yeah. So this is the power system. The most of these vessels are powered by electrical systems, especially the new vessels. They are hybrid. Sometimes the generator a battery combination or fuel cell battery combination. So these are the new technologies. So today's topic is not the hybrid system. So I just give a thing like that. And these are very new technology or the very efficient the, and optimize the system. In order to optimize this system, we use for battery and things the energy management system. So automated system again. And now currently we have this most of the vessels, so DP vessels or advanced vessels have the power management system. So the power management system can stop these generators. These generators, there are four generators here. If, for example, if you close the bus tie breaker with all the protection, it's one system. So we can use less number of generators to feed these thrusters. And in case any power demand due to the weather condition, whatever reason, higher demand, the power management system automatically start the standby generator if they are on the remote mode or standby mode. For example, if the engineers put this on local mode, power management system cannot start this thing. So that's very important, right? And yeah, that's basically a simple idea of what the. In addition to there are machinery systems, cooling systems, fuel oil systems, lube oil systems, ventilation, and all kind of auxiliary systems. Those are also very important to maintain this equipment. So I'm not going to talk much about those areas today. Uh, Next slide is now the consideration upgrade. So that actually most of the thing in this slide I have spoken earlier. We need to see what are the systems that are actually suitable on the current state to be worked on the remote from control from the remote control center, and what are the additional control systems that are needed. Some of the things I recognize is actually monitoring and control of safety systems because that is a totally independent system. The person at the remote control should be able to see those functions. You know, they have fire detection system, a gas detection system. If it's a gas, for example, if the vessel has a fuel cell and things like that, there should be a gas detection system. All these systems have to be integrated into the remote control center. So that's another requirement. And the video footage, you know, or the cameras, you know, this is also again not a new technology. Most of the vessels have CCTV, especially passenger vessels. They have they are covering the entire ship with CCTV, the closed circuit television TV system, and they have been the cameras are located everywhere, so we can see the same information or upgraded system can be used for this vessel. And there are other ways of getting the outside, the lidars and things like that. So it's a vast area again. Yes. Now look at the risk areas. Yeah. So this is something that we are actually worried about. People have to. I mean, everyone has to take concern because everything has to be operated safely without damaging the environment, assets, or anything. So therefore, some of the risks that are I consider is cybersecurity, environmental changes. If the environment change and the vessel cannot sail through that environment, that will be a problem. And then RCC to mass communication and the failure of RCCs. I mean, failure within the remote control center, if that happens, so how is it the redundant system or redundant RCCs, communication and things, and the collision avoidance, these systems are already there, collision avoidance systems on board, radar and APA, automatic radar plotting system that can detect the collision before the vessel collides. So these things have to be improved or use these systems in the remote control center. So that's another thing. And the third one actually is the system failures. That is my main topic today. The system failures. If a system fail or component fail, how it is going to affect the operation of the remote control center, and can the remote control center control this vessel? If that failure happen, they need to have good assessment about the vessel. How good this vessel for this purpose? Yeah. So I have actually taken uh, some of the this data from the International Marine Contractors Association, that is IMCA, is doing a great job. They are writing guidelines for operating offshore vessels, and mostly offshore and DP vessels and things. And also they do a collection of all the incident or undecided event and observation every year, and they publish. And why they are, how they can get the most of the ship owners and operators are volunteered to give this information. Whatever incident or any undesired event or observation happen, they write to IMCA, and then IMCA collect all these things. So this year, so far up to August, so they have collected 84 cases. So out of 84, you can see that they also categorize into two levels, yeah, main cause and secondary cause. Main cause is the one that contributing to the uh, direct contributing to the incident or the undesired event. Secondary cause is the one that lead to the main cause. So that's how they categorize. So the yeah, propulsion system, we can see that there are 28 direct causes, propulsion and thruster. And then position reference systems, 17. Know what a position reference, GPS, everyone knows somebody, yeah? That's one of the position reference, failure of those things. And there are different type of position reference systems on these vessels, not only GPS, but there are local systems like side scan or laser system, radar system, and there are so many of them. So and then the computer failures, they got 16 computer failures. And then the power, that's the power generation part, and then environmental conditions, not much actually, 4 cases. That means the environmental condition was higher than the vessel's capability. So that's the way. So that means, and then human factors. So there are only three direct human factors, but there are 17 that have led to the main cause to have this incident or undesired event or observations. And the electrical also 21 cases, that means the switchboard and things like that. And the other sensors like gyro, um, uh, wind sensors, uh, MRU, motion reference unit, and all kind of those sensors, and mechanical and uh, zero. Basically, there's no mechanical failure directly involved in any incident in this year so far. But there are secondary event, yeah, secondary causes. So these are the things. Now this figure, actually, all these vessels have been approved by class. They look at the system, the safety and everything. go by it, and each drawing they check and then approve. I myself know because I have been a class surveyor or class approval engineer, so I used to do all these things. But how much they can check? That is the question. So it had to be genuine. The person who are designing thing had to be really genuine. And what level of review can be done at the class? That's a challenge. It's a huge challenge. And the other thing is there is another third party involved in writing the FME like ourselves. We are writing, analyzing the system failures. So it is important that systems have been properly analyzed and identify these critical areas. What are the things? And also the people operating this, engineers and operators, they have to have full skill. There are a lot of institutions like NI, they certify the operators who are operating the vessel. They have examination training. There are a lot of training centers. There are a lot of things in industry. And the industry guidelines are there like MTS, Marine Technology Society, IMCA. So if you follow all these things, we can reduce these things. The purpose of IMCA to produce this or to publish these things that people to understand. So there is something wrong. We need, or if not wrong, need to improvement of this system, current system, to avoid these things. We want safe world without any incident, anything. Because this, when the vessel goes, the danger can go into loss of lives, loss of assets, environmental damage. There are so many things you can see in the industry. So many things have happened. So in order to avoid that, we need to have very robust systems that can handle all these things. They have the technology, and then we need to apply them properly and then get that thing. So that is very cool. So I will give few of incident get into detail. This is more technical. Don't worry about that. But I try to explain as much as possible how this happened, where are the problems. Like, just examples of things, not much in this. So this is actually one incident that happened due to uh, human error. So this vessel, you can see that this is a family, no? Four. This is my favorite diagram: four thrusters, 1, 2, 3, 4, and two switchboard, and that. Yeah. So what happened was this vessel was waiting outside 500 meters. So normally in offshore we can categorize 500 meters near a platform. This was outside a glass platform. I took this from IMCA uh, publication. I don't know, this happened in 2018 or 19. Um, so when the while waiting for the orders from the platform to go inside, and what the crew on board did was they closed the bus tiebreaker and they used only one generator to and then three thrusters. So they were waiting. Okay, the weather was okay, and then they were waiting there without. No, weather was actually 40 knots, 30 to 40 knots as per the record ISO. So they anyway they are not taking. They say they can afford to lose position, but they didn't know what the consequences. If you look at here now, what happened is when the service engineer was doing some routine maintenance, he accidentally activated the emergency stop of the running generator. So then there's only one generator connected to the single bus, and then there is no power generation. It went on blackout. The vessel totally lost the complete power, and then they had to start the generators remotely, and then they had to took a lot of time to get that this. And this is actually not a recommended way to do that. This is considered a human error, and therefore now when if you look at this kind of a vessel now control from a remote control center. Remote control operators, whoever is there, we don't know yet how they are the programming. They are the technical team and the operator team. However, it is they have to have fully understanding about what the risk of this system now. We consider like this, and ideally they should have kept one generator on one side, then it's safe in case something happens. Okay, one generator fail or something, and then other section will be there to maintain position. It will not go to blackout. So that's something to be considered. And the second incident is a failure again. It's a governor failure. You know what a governor is? In a generator. Uh, uh, the governor is basically controlling the speed of the engine. To give the more power, you increase the the fuel rack, you open more fuel to the engine, and then it will go. So that's the governor. So governor failure incident. So this was operating on closed bus again, and this is the bus tie I showed you. This is closed, and then two generators were running, three generators online, one was standby, this one. And then what happened was one of the generators, this one, I think DD2, got the governor stuck up, the mechanical part, in the I call it activator, was stuck up at the highest level. That means it opened the full fuel to the engine. So engine will try to put the full power into the system. So what happened was other generators are working in synchronization. The control system of the other generators reduced the the governor for the speed of the thing, and then finally it won't, because this power is so much that this generator was feeding these four thrusters, plus they have excessive power. So this excessive power was trying to drive these two generators on a reverse power. That means the power is flowing in the other direction. So therefore there is a protection called reverse power protection on these generators. So the reverse power protection, when it exceeded the set value, it tripped these two generators. So now what happened was only the DG2, which is at fault, was only fed in this one. So now what happened next? The thrust demand or the power demand increase after some time, and then DG4 started. But it was too late. Before it started load sharing, this trip, the DG2, which was the faulty one, was tripped on overload. That is another protection system. So therefore, it led to blackout again. This is a system failure. But we don't know whether what kind of protection this vessel has. Yes, and then DG2 normally have protection for governor. They can identify these failures and trip it. Don't know whether they are. Somehow it did not work. Right. Uh, the next one is a crash synchronous. It's a similar system, but this was operated open bus. But uh, what happened was, for some reason, the bus tiebreaker closed without any activation by anyone. So that due to a signal, some failures. So we need to identify why it closed. So it should not have closed. Yeah. Okay. So this is actually this may be too technical to explain this one. This is how actually one of the systems. This is a control system. So therefore, this, if you can see that there's a single failure here. This is the bus tiebreaker Q1. I said this is the control system, and it could have been something like that. This I have seen this type of systems on board. So this is a design failure. So this should have been identified at the beginning. So right. So basically, yeah, that's the end of presentation. Let's talk about the conclusion very fast. Basically, this is an emerging system, but the autonomous system, but the current systems are matured, but still there are things happening and incidents and then as per IMCA, and familiarization of the human error is needed. Actually, the human error should be improved by familiarizing with the systems, and the challenges of mast design the rubber system. That's another challenge. And then RCC operators should be fully knowledgeable with what they are doing, and also the classification societies to be very much uh, knowledgeable about the thing, and if there are new thing they need to be trained, and then the managers have to be this. So, yeah, and the future work, actually this is a very good system. Actually, it's the system is the technology is evolved, developed, and what is needed is to reduce these system errors, human errors, and things that can be improved by really considering these failures and then improve the system. Technology is there. What is important is to take serious and then design robust systems, and all the people who are involved in that should be able to consider that. And yeah, technology is improving and fast growing market, and this is really good sun, and then you can operate economically, and all good things are there. And then the important thing is to operate them safely. That's the thing. Thank you very much for listening to me. And then I would like to take any questions if you, sorry, afterward, after. Okay, then the questions will be afterwards. So I would like to introduce my colleague Wayang. So he will take the lesson. Okay. Thank you.
Right, thank you, Sen, and good morning, everyone. Welcome to the October Rex Files. Now, what are the ABL case reports? The purpose of this section of the briefing is to simply keep you updated on some of the recent higher cost incidents that ABL has been involved in, and in doing so, show you some sorts of incidents and casualties that can happen in shipping and marine operations. These feature largely, but not exclusively, hull and machinery casualties, with estimated costs of repair in excess of $250,000, usually excluding the salvage costs. They cover only a subset of the total ABL caseload. Typically, this is in the order of 10%, and it is an important subset, which represents about 25% of the H&M cases by number, and around 65 to 75% of the H&M cases we survey by cost. The estimated costs are often preliminary and subject to further inspections and/or investigations. In presenting these case reports for last month, it's not about attributing blame. There will not be specifics of cause, as many are still fresh and it wouldn't be appropriate. And in many cases, the cause is still under investigation. A copy of this presentation or a previous one is available on request. Now, as usual, let's start off with some statistics. Starting from the left-hand side, the majority of cases we were instructed on in September were again engine room or the ER machinery cases that you can see. There was one grounding, a couple of fire explosions, a couple of collision elisions, a couple of thruster cases, a tail shaft seal case, and a few others on lightning, crane failure, and theft. In terms of the cost for September, we can see that the pair of fire explosion cases dominated the figures for the month, and while engine room machinery cases had the majority by number, these were by comparison a smaller amount of the total costs for the month. The average cost for the month is approximately 2.8 million, which is much higher than last month's average total of about 1.2 million, and the highest since April. The typical annual background expected figure is about 1 million per high cost casualty when extremes of over 50 million are excluded. The overview of 2021 to date shows that engine room machinery cases still continue to be the most common cases that we work on, and this graph shows that there continue to be healthy instructions on a variety of work, and that includes groundings, fire explosions, collision elisions, and other cases also adding to the total. This graph looks at the total costs for the year, and it shows that fire explosion cases now exceed the high cost sinking cases that previously dominated the chart this year. The annual cost distribution is mainly comprised of more than 30% in fire explosions, another 30% in sinking capsizing, and about 20% in engine room machinery cases so far for 2021 to date. The overall average cost for the year for our high cost cases currently sits at just under 1.5 million. Let's move on to some of our cases in a bit more detail. First up for September, we have this approximately 10,000 deadweight ton cable layer that was engaged in sea trials for fiber optic cable when an oil sheen was noted in the vicinity of the starboard thruster. The unit and its associated lubricating oil pumps were secured and the oil system static head pressure lowered in order to minimize and isolate the leakage. The vessel returned to port for disassembly of the unit and damage investigation that is currently underway. Upon opening the unit initially, metal particles were found in the lubricating oil and associated space in the thruster. And you can see here the disassembly that's still underway. And so far, the damage that has been noted has been as follows. Damage to the thruster seals, contamination of the oil charge, also all lube oil piping and thruster lube oil systems due to the metal particles, fracturing and pitting of the pinion drive gear teeth, pitting of the bull gear teeth, scoring of the forward and aft thrust shoes and of the thrust surfaces, pitting of the babbitt bearing face and inside that's inside the shaft bearings. Damage to oil seals and liners in both the steering seal box and propeller seal box due to contact with metal particles, and scoring damage to the upper and lower thruster unity bearing races, with the upper bearing race losing 2 rollers due to scoring. The following repairs are intended to be carried out whilst the vessel has been dry docked and the thruster removed. The thruster unit will be completely disassembled for inspection. The interior of the unit and all parts are to be cleaned, inspected, and the metal particles removed. Piping and pumps are to be flushed with clean oil. All affected oil seals are to be replaced. Also, the pinion gears, drive motor, bull gear, 22 thrust shoes, and babbitt bearing are to be replaced as well. The scored shaft extension and thrust plate faces are to be skimmed, and the oil charge will be renewed. No formal allegation of cause has been made so far, although in all likelihood there was an oil seal failure. The failure of the oil seal was most likely as a result of being exposed to metal particles in the lubricating oil system, but it is still unknown where this would have originated from. The problem with such failures are the extensive lead times that are involved, up to about 31 weeks for steering motors and 91 weeks for the bull gear. The opportunity has been taken in this case to ship 2 containers of thrust spare parts to be used in the repair of the unit, and the items not used for the repair will be kept in storage upon completion. This decision was based on the shipping cost for the spare containers having to amount much less than the downtime that would have been incurred whilst waiting for new parts to be manufactured and shipped. Furthermore, the number 2 pinion, as you can see in this photograph, will be sent for metallurgical analyses, and that includes hardness testing, and that's to assist in ascertaining the cause of the damage. It's been noted that the levels of iron that were standard for all 6 of the vessels in this particular fleet, and there has been no previous signs of metal shown whilst changing out of the oil filters as part of their routine maintenance. Once the affected parts have been replaced, the thruster will be reassembled and refitted in position, and the vessel returned to water for finalization of repairs. The next case is this approximately 7,100 deadweight ton roll-on, roll-off vessel, as was reported in early September. Whilst en route during a regular voyage, a fire alarm sounded on the bridge, and the engine officer on watch reported thick smoke over the number 2 main engine on the port side. The general fire alarm was activated, and the captain attended the bridge. The third mate took over navigational watch, and the crew mustered at the designated muster station. 3 fire hoses were arranged, and the emergency fire pump was started as per the ship's contingency plan while the vessel was still adrift. Fuel supplies to the main engine were shut down, and the emergency generator was started. All hatches, vents, entries, and doors of the main engine control room were closed, and the fire was localized to main engine number 2. All passengers and crew were checked to be safe. Then, at the captain's command, the CO2 system in the engine room port side was activated, and the crew commenced cooling of the adjacent bulkheads, walls, and main deck. 2 crew members in full fireman outfits entered the engine room to check that the fire was extinguished. Cooling of the bulkheads, wall, and main deck continued, and all doors, hatches, and vents of the engine control room were reopened for ventilation. A check was made on the atmosphere inside the engine room using portable gas detectors, and engine levels were found at 21%. Further investigation performed by the crew revealed that turbocharger of the main engine number 2 was blown up, and attempts to recover the system for starting the air pressure and fresh water cooling systems then began. 2 watchmen were placed on duty at the location of the fire. The freshwater cooling system was then recovered, and the air compressor was connected by cable with emergency diesel generator for air intake. Diesel generator number 2 was started, and preparation for starting main engine number 1 on the starboard side began. Tugboat was sent for the rescue operation in the meantime. Then diesel generator number 3 was started, and preparation for starting of main engine number 1 continued further. After about 8 hours from the fire alarm, main engine number 1 was started, and the vessel was underway again. For the main engine port side, the extent of damage found included the main engine port side in the way of first deck and tank top was found partly burnt. All exhaust valves were found with signs of overheating. Exhaust valve actuators were found overheated. The turbochargers was found melted and broken. High pressure fuel oil pump of all 6 units were found overheated with melted reverse cylinders. The high pressure fuel oil pump unit 5 puncture valve was found torn and missing. Governor was found melted. All pipes of the remote and local control systems were found melted. Cylinder lubricator was found partly melted. Auxiliary blower was found overheated and melted. Electrical motor and switchboard. The oil mist detector was also found melted. The main engine cooler was found overheated. All cables and sensors were found destroyed. The piping and sealing of the main engine cooling, lubricating, oil, air, fuel, and steam systems were found variously damaged. The turning gear was found burned, and the main starting air valve was also found overheated. Damages were also found in the engine room portside first deck workshop and portside main engine compartment. There was also damage as a result of heat, smoke, and efforts to extinguish the fire. The permanent repairs are in progress by local gangs proceeding with repair works using a safe berth. For the main engine portside, the necessary repairs to damage as a result of fire, smoke, and heat include: the main engine portside is to be fully dismantled, all damages to be identified and completely overhauled. All overheated and melted parts are to be renewed. The turbocharger and governor are to be renewed. All pipes of the remote and local control systems are to be renewed. The auxiliary power blower is to be overhauled. The oil mist detector is to be renewed. The air cooler is to be inspected, cleaned, and repaired as necessary. And apologies. It's going back one. All cables and sensors are to be renewed. The main engine turning gear electric motor is to be renewed, and on completion, the main engine is to be tested and sea trials to be carried out. Including the repairs and damages also found in the engine room portside first deck workshop and portside main engine compartment, it is estimated that the permanent repairs will require about 30 working days at safe berth, excluding time for delivery of spare parts and subject to no additional damages found. Another case in September was this approximately 2,700 deadweight ton general cargo Elysian. The vessel left locks and was headed west with the master at watch. The chief mate was about to relieve the master with the helmsman and the pilot present as well. The helmsman reported that the rudder was not responding and that it remained at 15 degrees to port side. In an attempt to counteract the non-responding rudder, the master overrode the steering with the manual hard to starboard whilst adjusting the controllable pitch propellers to full astern. At the same time, the bow thruster was ordered full to starboard in order to provide sufficient water flow over the rudder for steering capability. Brief engine ahead movements, kicks were also given. The vessel did not respond sufficiently and kept on swinging while proceeding ahead, and as a result, the vessel alighted with a fixed quay side at approximately 8 knots, and the vessel suffered damage to her fore peak. The vessel eventually maneuvered away from the quay at her own power and berthed nearby at another quay. During this time, it was reported that the rudder was responding normally again. As can be seen, the forward bow of the vessel is damaged. The shell burst and buckled at locations on both the starboard and port sides. The internal stiffening structures were deformed and buckled, and vertical stiffeners were broken. The damage is observed from the main deck level, with the stem and shell plating torn and split at the weld seam running approximately 1.3 meters aft. The adjacent bulwark and intermediate frames were also buckled. Inside, between the main deck level and first stringer deck on the starboard side, the major frames 169 and 173 were bent. The intermediate minor frames 170 to 172 were also bent. Centerline swash bulkhead between the main deck and second stringer deck between frames 169 to 173 were also buckled. A level stringer deck forward of frame 173 and another forward of frame 175 are buckled and require renewal. Breast hooks at different levels also require renewal forward of frame 175. With damages found below the waterline, repairs will be carried out in 2 stages. The first stage is ongoing for the permanent repairs above the waterline, and that's going to be along with the temporary repairs below the waterline. The second stage will be the balance of the permanent repairs below the waterline that will be deferred until the next scheduled dry docking. The damaged steel will need to be cropped and renewed, and that is estimated in the region of about 8 metric tons. The welds must be subject to non-destructive testing in accordance with classification rules. Due to the extent of damages, all affected tanks may also require pressure testing. Upon completion, all damaged and adjacent areas will require to be recoated in accordance with the vessel's paint coating system. It is alleged that the damage forming subject to this case was a result of malfunctioning rudder. It is noted that steering gear motors driven via electronic variable frequency drives, VFD. Both units are fitted with an alarm log, however, neither recorded any fault. The investigation continues on this case. Last for this month is this without prejudice survey on behalf of vessel interests at the quay that was allied with as described in the previous matter. The full extent of the damage is difficult to estimate as the full underwater condition of the quay has not fully been established, although an initial outline diving survey has been carried out. The initial details of how the quay was built is not clearly defined. However, it appears that the original construction is a concrete or stone block wall with a concrete capping beam and apron. The entire length of the quay has a lower access added, which appears to have been constructed by a complete run of interlocking sheet piles installed approximately 1 meter in front of the original wall. The intermediate space has been backfilled with sand and a concrete cap added with wooden decking partially installed over the surface. The walkway sheet pile worn is torn. It is bent and partially absent over approximately 12 meters. There appears to be damaged concrete and steel tie rods behind the steel sheet pile wall and on the original wall for approximately 3 to 4 meters. This breach has allowed backfill material to become removed, although the extent of the backfill loss is not yet known, and the condition of the backfill will need to be advised by further sounding and diving investigations. A full diving survey still needs to be carried out to determine how much backfill material may have been lost and whether there has been further damage to the original wall. While no misalignment of the main quay edge or crane railing or new cracks on the quay have been noticed at this time, this may potentially develop due to the loss of backfill material. The crossover bridge between the quay and a pontoon has been seriously damaged. The bridge has a length of approximately 4 meters with steel beams, wooden planks, metal access, and handrail. The steel beams have been twisted and bent. As you can see, the wooden planks covering the bridge have become detached, and the metal handrails and access leading from the quay to the crossover bridge have also been damaged. No damage to the working pontoon was noted, but it was unable to be accessed for the survey at the time of this inspection. The repairs, now if no further damage to the original wall are found, are expected to include removal of the concrete capping, renewal of the sheet piles, excavating backfill, renewing tie rods, renewing backfill, and renewing concrete capping and apron. The crossover bridge will also need to be lifted out and replaced. As with the vessel, the investigation continues on this case. And that's all I have for you for this month. Thank you all for your attention, and I will pass you back to Matt.
Thanks very much to both the presenters today. That was very interesting. Because we've run out of time, we've already run a little bit over. Can I please ask that any questions be submitted via email, and then Sen can get back to you on email. That will give us a bit more time to respond. The next market briefing is going to actually be on the 3rd Thursday of next month, because we've got a scheduling conflict coming up. We're usually second Thursday of the month, but the next one is going to be on the 3rd. So that will details of that will be going out soon. Because we're back here in person, of course, we've started asking our questions again. And I did have somewhere there it is. Thank you. Can you just pass that to me? So last month we asked a question based on the technical presentation, and the winner of our the questions, and the ones who got it right, there weren't that many, so obviously not many people were paying attention. Only 3 people got it right, and the winner drawn randomly from the hat is Paul Cunningham. But I don't think Paul is here today, although he did say he'd be here, so I shall be having words. So I guess I'll have to march through the market later on with this in my hands and take it to his office. So thanks very much, everybody, for coming along, and we will see you on the 18th of November next month. Thanks, everybody.